Welcome to Akbar Academy. Today we are going to look at the Cambridge IGCSE Physics Syllabus 0625, Summer 2019, Paper 4, Variant number 1, question number 1, and it's all about motion. So let's get stuck right in. A rocket is stationary on a launch pad at time t equals 0. The rocket engines are switched on and exhaust gases are ejected from the nozzles of the engines. The rocket accelerates upwards. Figure 1.1 shows the acceleration of the rocket, how the acceleration of the rocket varies between times t equals 0 and times tf. So this is kind of quite rare. You get acceleration time graphs quite a lot in paper 2, but paper 4, not so much. So this is quite a rare graph. And the very, very first question says define acceleration. Now, here's what I want to say to you. A definition should be said in words. However, the syllabus, the exams do allow you to say the formula in words if you're struggling with the definition itself. I'm going to give you both. The one thing I would not do, even though I know they allow it in this question, is just to write the formula in symbols. Now, like I said, they do allow you to do it in this question, but I know of many, 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 many questions where they don't allow that. So either write the definition in words or write the formula in words. So what do I mean? Well, the definition itself is rate of change of velocity. That's the actual definition. That's what acceleration is. If you wanted to write that in words, it would be acceleration equals final velocity or speed minus initial velocity divided by time. Okay, so those are your two options. Like I said, in this question, they do allow E equals V minus U over T, but I'm suggesting strongly that you steer clear of that because there are way more questions where they do not allow this. Next part, and the part that most students, many students would find quite challenging. On figure 1.2, sketch a graph to show how the speed of the rocket varies between time t equals 0 and times t equals f. Now, the key here is to basically go back up and look at the graph and try to understand what's going on. If we look at the first part of the graph, the diagonal part, basically the acceleration is increasing. In other words, the speed is increasing. No shock there. However, if you look very carefully at this part, that is basically saying constant acceleration. Now, students should be very, very familiar with what constant acceleration looks like in a speed time graph. If it was a speed time graph, constant acceleration would look like this, or starting from 0, but I'm deliberately not starting from 0 because quite clearly when we get to constant acceleration in this graph, it'll be a non-zero value. So most students would know that part, meaning the initial part should look like this. It should be curving up the way. Why? Because the acceleration is getting bigger and bigger and bigger. In other words, the speed is going to get bigger and bigger, and the gradient's going to keep increasing on the speed time graph. So if we stick these two ideas together, and what should happen, and I'm going to struggle a little, is let's just see how far across. Okay, a couple of centimeters. So what I'm going to do is basically make it curve up and then make it go straight. That's not a very good job. Let me try that again. So let's make it more exaggerated. So curving up the way and then straight. Okay, so just to be clear, this bit in here should be straight diagonal line. This is more a note for you. In other words, in math geek speak, constant gradient. Whereas here it should be curving up the way and in math geek speak, increasing gradient. Next, sometime later, the rocket is far from Earth, and the effect of the Earth's gravity on the motion of the rocket is insignificant. In other words, it's so small, it's negligible, we can ignore it. As the rocket accelerates, its momentum increases. State the principle of conservation of momentum. So this is basically knowledge and understanding. You've got to remember this. You've got to remember the definition. And most students would get the first part, but probably miss out the second, which is total momentum before equals total momentum after. Now that's a bit most students would get, provided there are no external forces acting. Now that is the definition of the conservation of momentum. And then it looks like last but not least, explain how the principle of conservation of momentum applies to the accelerating rocket and the exhaust gases. Now, when we do examples like this at IGCSE, it normally involves collisions where we've got maybe one car crashing into another car or two objects basically colliding with each other. Here, it could be a bit more confusing for a student. They're like, well, what's happening with the rocket? How is there momentum before and momentum after? I'd like to give you two kind of examples. Imagine blowing up a balloon, making it nice and big, and then letting the balloon go. Hope you understand the balloon will end up going flying around the room. Why does that happen? Because the rubber nature of the balloon will compress the gas in the balloon. The gas will leave the back of the balloon, so the balloon pushes the gas back in order for the balloon to move forward. Now, that's me simplifying that because as we know, the balloon will just, rapidly go around the room. Another example I'd like to give you is, imagine you're swimming in a swimming pool and you're doing the breaststroke. We would push the water behind us and the water would end up pushing us forward. So the key here is to understand that the rocket's got an upward momentum and the gas has got a momentum in the opposite direction because it's been expelled in the opposite direction. It's been given out in the opposite direction. So the rocket has an upward momentum. The ejected gas has an equal and opposite momentum. In other words, the rocket's going up the way and the gas is being expelled down the way equally and opposite.